For centuries, humanity has gazed upon Jupiter, the colossal king of our solar system, and seen a majestic, unwavering sentinel. It stands as our solar system's colossal guardian, its immense gravity a shield, deflecting countless comets and asteroids that might otherwise imperil the inner planets, including our own fragile Earth. But this grand, benevolent image, so deeply ingrained in our collective consciousness, is deceptively incomplete. It obscures a reality far more complex, more violent, and paradoxically, more life-giving than we ever dared to conceive. How can a world so hostile, so utterly alien, simultaneously forge the very conditions for life? This profound question began to unravel in 1958, a pivotal year that reshaped our understanding of the gas giant. Using data streamed back by the pioneering Explorer 1 satellite, the brilliant American physicist James Van Allen made a startling discovery. Jupiter was encircled by vast, invisible belts of trapped radiation, far more intense and pervasive than anything found around Earth. These belts, later named in his honor, create an environment of lethal energy, a veritable maelstrom, so potent it could cripple unshielded spacecraft in mere hours and shred complex organic molecules into their most basic components. This zone around Jupiter is, without hyperbole, one of the most hostile environments imaginable within our cosmic neighborhood. Yet, here lies the extraordinary paradox. This very same immense source of gravitational and magnetic power, which creates such a deadly embrace, is also what transforms Jupiter's icy moons into potential abodes for life. It is a concept that fundamentally challenges our classical understanding of a habitable zone, a region usually defined by its proximity to the Sun, where warmth allows liquid water to persist. Jupiter offers an alternative, a localized crucible where life might thrive, not despite the violence, but because of it. The scientific community grappled with this enigma for decades, seeking the underlying mechanism that could provide internal warmth to these distant, frigid worlds. Then, in 1979, a groundbreaking paper published in the prestigious journal Science provided the mathematical key. Authored by Stanton Peele, Patrick Casson, and Robert Theodore Reynolds, this work meticulously modeled a process known as tidal heating. It described a relentless gravitational kneading of the moons as they dance in orbit around their colossal parent. Imagine the immense gravitational pull of Jupiter, stretching and compressing its moons like a cosmic stress ball, first from one side, then another, as they follow elliptical paths. This ceaseless, titanic tug-of-war generates immense internal friction, converting gravitational energy directly into heat deep within the moon's rocky cores and icy mantles. This process, far more powerful than the faint warmth provided by the distant sun, is enough to maintain vast, global oceans of liquid water, hidden beneath kilometers of frozen ice. Jupiter, in this profound sense, functions as a gravitational star, its titanic pull radiating a form of energy that rivals the Sun for its closest orbiting bodies, carving out a separate, dynamically sustained, habitable zone in the outer reaches of our solar system. This constant geological turmoil, driven by Jupiter's colossal gravitational embrace, is more than just a source of warmth. It is the engine that could power hydrothermal vents on the floors of these subterranean oceans. These underwater fissures, spewing mineral-rich, superheated water from the Moon's interior mirror the very environments where many scientists, including the renowned geochemist Michael Russell, propose life on Earth may have originated. On our own planet, the deep ocean vents teem with exotic life forms that thrive not on sunlight, but on the chemical energy derived from these volcanic outflows. The implications are staggering. The conditions for life are not always found in serene, stable environments, bathed in gentle starlight. Instead, they can be forged in the very heart of cosmic violence, transforming a desolate zone of death into a vibrant cradle of possibility. For centuries, the cosmos has challenged our perceptions, revealing worlds stranger and more wondrous than any fiction. We seek the grand, the obvious, the photographic proof. We scan the skies for volcanic eruptions, for vast rivers, for the telltale glint of light off liquid water. But sometimes, the most profound revelations come not from the visible, but from the invisible. It was an ethereal whisper, detected by a machine traveling hundreds of millions of kilometers from Earth, that first betrayed the existence of vast, hidden oceans on Jupiter's icy moons. This was not a geyser caught mid-eruption, nor a shimmering sea observed directly. This was a secret uncovered by a ghost. The year was 1995, when the Galileo spacecraft, a marvel of human ingenuity, finally arrived at the colossal realm of Jupiter. For 8 years, until 2003, Galileo meticulously orbited the gas giant, conducting a painstaking orbital tour that would redefine our understanding of the outer solar system. At the heart of this detective story lay a crucial instrument: Galileo's magnetometer, a device designed to measure magnetic fields. Its principal investigator, Dr. Margaret Kivelson of the University of California, Los Angeles, and her dedicated team found themselves grappling with data that seemed, at first glance, utterly bizarre. As Galileo swept past Europa and its giant sibling Ganymede, the magnetometer registered a peculiar anomaly. These moons, seemingly inert balls of ice and rock, were generating their own weak, temporary magnetic fields. This was no static phenomenon. These induced fields were fluctuating, pulsing in direct response to the immense rotating magnetosphere of Jupiter itself. It was as if Jupiter was performing a cosmic ballet, and its moons, deep within their icy shells, were somehow responding with an invisible magnetic echo. The question reverberated through the scientific community: how could these small, icy bodies create such a phenomenon? The answer lay in a fundamental principle of physics known as electromagnetic induction. To grasp this profound discovery, consider the workings of something familiar, like a simple electrical generator, or even the wireless charger on your phone. In both cases, a powerful, fluctuating magnetic field is the primary driver. Jupiter, with its immense size and rapid rotation, possesses a colossal, powerful, and rapidly rotating magnetic field. Think of this as the primary current, sweeping through the space around it, encompassing its moons. Now, as this powerful magnetic field washes over Europa and Ganymede, it interacts with whatever lies within them. If, and only if, there is a significant layer of electrically conductive material inside these moons, Jupiter's sweeping field will induce a secondary magnetic field. This induced field is a direct consequence of the primary field causing electrical currents to flow within the conductive material, much like how a changing magnetic field induces a current in the coils of a generator, producing electricity. The specific signature and strength of the magnetic fields detected by Galileo pointed to only one plausible candidate for such a conductive layer: a globe-spanning ocean of salty liquid water. Salty water, rich in dissolved ions, is an excellent electrical conductor. Pure water, by contrast, conducts electricity poorly, meaning the ocean beneath the ice had to be briny. This was the smoking gun, the definitive evidence, a magnetic ghost, that revealed the presence of an ocean hidden beneath kilometers of ice. The late 1990s were a period of intense scientific debate, a thrilling convergence of disparate lines of inquiry. As the magnetic data from Galileo poured in, scientists were also analyzing visual evidence from Europa's surface. Images revealed a world covered in a chaotic, broken landscape, marked by vast chaos terrains, where blocks of ice appeared to have shifted, rotated, and refrozen, along with a network of long, linear cracks stretching for hundreds and even thousands of kilometers across the moon's face. These visual clues suggested a dynamic, active interior, with subsurface motion that could only be explained by a layer of liquid beneath the ice. The magnetic evidence, hinting at a conductive ocean, perfectly complemented these visual observations. Two entirely different scientific approaches, one observing the surface, the other probing the unseen magnetic realm, converged on the same astonishing conclusion: Europa, and potentially Ganymede, harbored vast hidden oceans. It was a testament to how modern planetary science often relies not on direct observation, but on interpreting the subtle disturbances in invisible fields, turning faint echoes into revelations about the hidden nature of distant alien worlds. The air itself bites, a frigid, alien breath at the bottom of the world. 2,000 kilometers from the nearest coastline, shrouded beneath the immense, crushing weight of East Antarctica's ice sheet, lies a realm of perpetual darkness, cold, and unimaginable pressure. This is a world sealed off from the sun's warmth for millions of years, a true geological time capsule. Before humanity could dare to cast its gaze across hundreds of millions of kilometers of void, towards the distant, icy moons of Jupiter in search of life, it first had to prove that life could endure in such an extreme environment. The proving ground was not on Europa, but here, on Earth. This is the story of Lake Vostok, Earth's most isolated and, perhaps, most alien ecosystem, a place that became the perfect terrestrial analog for the hidden oceans of Jupiter's moons. Buried nearly 4 kilometers beneath the frozen surface of the Antarctic continent, Vostok is a liquid world utterly cut off from the dynamic processes of our planet's surface. Its discovery, an accidental triumph of scientific persistence, began not with a search for alien life, but with a quest to understand Earth's past climate. In the 1970s, Russian scientists at Vostok Station, one of the most remote outposts on Earth, began a monumental undertaking, drilling ice cores deep into the ancient ice sheet. Their primary goal was climate research, painstakingly extracting cylinders of ice that contained trapped air bubbles and dust, offering a frozen record of Earth's atmosphere stretching back hundreds of thousands of years. As the drills burrowed deeper, past 3,500 meters, then nearing 4,000 meters, something extraordinary began to emerge from the data. By the 1990s, seismic surveys and radar data unveiled a startling anomaly beneath the ice. The readings indicated a vast, smooth, liquid body, not rock, not ice, but water. A colossal freshwater lake, stretching over 250 kilometers long and 50 kilometers wide, with depths reaching more than 1,200 meters, lay hidden beneath the ice. This was not merely a puddle, but one of the largest freshwater lakes on Earth, untouched by sunlight or surface contamination for an estimated 15 million years. The scientific community was gripped by a revelation. A buried world existed right under our noses. The decades that followed saw a technologically arduous and often controversial Russian effort to reach this pristine environment without contaminating it. The challenge was immense, drilling through nearly 4,000 meters of ice while ensuring that the drilling fluid, a mixture of kerosene and freon used to prevent the borehole from freezing, did not breach the lake's pristine waters. Scientists grappled with this ethical dilemma, understanding that any contamination could destroy the very ecosystem they sought to study. This delicate dance of engineering and environmental preservation served as a direct, invaluable dress rehearsal for any future mission to the icy depths of Europa. The stakes were not just scientific, but existential for the potential life within. Then, a breakthrough moment arrived in 2012. After more than 20 years of painstaking effort, the Russian drill finally breached the surface of Lake Vostok. It was a victory hard-won, marked by the drill's temperature sensor detecting a sudden increase in heat as it entered the liquid water. The initial samples retrieved, however, were not of the lake water itself, but of the refrozen lake water that had risen into the borehole. This frozen column was then brought to the surface, preserving the pristine nature of the lake below. Subsequent genetic analysis of these retrieved water samples, championed by researchers like Dr. Scott O. Rogers, revealed a surprisingly complex and diverse ecosystem. Scientists identified over 3,500 unique deoxyribonucleic acid sequences, representing a wide array of life forms, from bacteria and archaea to fungi and even more complex multicellular organisms. This groundbreaking discovery proved, unequivocally, that life could thrive without sunlight, without the energy from photosynthesis, relying instead on chemosynthesis fueled by minerals leached from the rocks below. It was a tangible, powerful proof of concept, the Vostok Protocol, providing a solid, scientific basis for the audacious search for life in Jupiter's hidden seas. What if the very definition of a moon, a celestial body orbiting a planet, is incomplete? What if one of these companions, dwarfing some planets, holds secrets that challenge our understanding of planetary formation and the very conditions for life? While its sibling Europa often claims the scientific spotlight with its tantalizing prospects of a hidden ocean, the colossal moon Ganymede presents an even more complex and profoundly mysterious puzzle. This gigantic world, the largest moon in our entire solar system, is unique in one extraordinary aspect. It is the only moon known to generate its own intrinsic magnetic field, a feature typically reserved for full-fledged planets like our own Earth. The monumental discovery of this magnetic field unfolded in 1996, a pivotal moment in the Galileo mission's extended tour of the Jovian system. As the spacecraft conducted its close flybys of Ganymede, Its sensitive instruments detected undeniable evidence of a powerful magnetic signature originating from within the Moon itself, not merely induced by Jupiter's immense magnetosphere. This was a triumph of engineering and scientific interpretation, confirming what many planetary scientists had speculated but could not prove. The profound implication of this detection was immediate and exhilarating. For Ganymede to generate such a field, it must possess a churning, convective liquid iron core, much like the molten heart that powers Earth's own protective magnetic bubble. This single revelation transformed Ganymede from a mere ice ball into a complex, fully differentiated world within a world, a miniature planetary system unto itself, far from the Sun's direct influence. Yet, the scientific revelations from Galileo did not stop there. The mission's data also indicated the presence of an induced magnetic field, an echo mirroring the one found on Europa. This secondary signal, generated by Ganymede's interaction with Jupiter's powerful rotating magnetosphere, strongly suggested the existence of a vast subsurface saltwater ocean. Salty water, rich in electrically charged ions, is an excellent conductor, perfectly explaining the observed magnetic fluctuations. This discovery painted a stunning and intricate picture of Ganymede's interior, a nested, multi-layered world unlike anything else we had encountered. Beneath its ancient, cratered ice shell lay not just a single ocean, but a complex tapestry of internal structures, including a liquid iron core, a surrounding rocky mantle, a deep liquid water ocean, and then the thick, icy crust. As our understanding of Ganymede's interior grew, planetary scientists began to theorize about its extraordinary complexity. In 2014, a groundbreaking model was proposed by Hauke Hussmann and his team, suggesting that Ganymede's deep interior might not harbor a simple monolithic ocean. Instead, they theorized a sophisticated club sandwich structure, a stack of multiple ocean layers, each separated by different phases of high-pressure ice. Under the immense pressure of Ganymede's colossal gravity, water can crystallize into exotic forms of ice that are denser than liquid water, allowing for layers of liquid to exist sandwiched between these high-pressure ice phases. This intricate layering would create a truly unique subterranean environment, a series of potential habitats isolated from each other by frozen, almost rock-like barriers. This intricate internal architecture stands in stark contrast to Europa's potentially simpler, single-ocean structure. Ganymede's Russian doll complexity, with its nested layers of ice and water, is further enhanced by its internal magnetic field. This field acts as a colossal shield, deflecting some of Jupiter's incredibly harsh radiation from reaching the Moon's surface and potentially its deep oceans. While the exact interaction between this intrinsic magnetic field, the subsurface oceans, and the Moon's surface remains a subject of intense research, it offers a compelling hypothesis. Ganymede's unique magnetic protection could create a different, perhaps even more hospitable environment for life to arise, an environment partially insulated from the cosmic bombardment that sweeps across the Jovian system. Ganymede is far more than just a bigger Europa. It is a unique planetary anomaly, a celestial body that stretches the very boundaries of what we conceive a moon to be, and a potential haven for a completely different kind of habitable environment, awaiting exploration. Knowing that oceans of water might exist beneath the frigid shells of Jupiter's moons is one thing. Reaching them, however, is a challenge of monumental proportions, pushing the very boundaries of human engineering and ingenuity. We stand on the precipice of an interstellar dive, but the path to these alien seas was not forged in the vacuum of space, nor in the gleaming laboratories of the 21st century. Rather, the conceptual foundations for such audacious missions were laid decades ago in the crucible of a global ideological struggle during the Cold War. In 1970, deep in the stark, frozen wilderness of the Kola Peninsula, in what was then the Soviet Union, a scientific endeavor of unprecedented scale began. This was the Kola Superdeep Borehole, a project born of a fierce scientific rivalry with the West, driven by the ambition to drill as deep as humanly possible into the Earth's crust. For over 2 decades, teams of Soviet engineers and geologists pushed the limits of drilling technology, plunging a narrow shaft downward, kilometer by painstaking kilometer. Their goal was not to find oil or gas, but to unlock the secrets of our planet's inner workings, to peer into its very heart. The challenges they faced were immense, almost unimaginable. As the drill descended past 7, 8, 9 kilometers, the rock became increasingly hot, reaching temperatures that soared beyond 180 degrees Celsius, a heat so intense it could melt the very tools designed to withstand it. The pressure was equally crushing, hundreds of megapascals, equivalent to the weight of a small mountain pressing down on every square centimeter of equipment. Drill bits, hardened steel masterpieces, warped, twisted, and shattered under these impossible conditions, leaving sections of the borehole orphaned and requiring elaborate retrieval operations or entirely new drilling paths. The drilling fluid, a critical component for cooling and lubrication, would sometimes simply vanish into unseen fissures. Yet from this colossal struggle against Earth's raw power, invaluable lessons were learned. The Kola Superdeep Borehole became a living laboratory for materials science, pushing the development of new alloys and ceramics capable of enduring extreme heat and pressure. It refined the art of remote drilling, teaching engineers how to operate complex machinery kilometers away, navigating blind through unforgiving subterranean landscapes. These were not mere academic exercises. The insights gleaned from the depths of the Kola Peninsula, the understanding of how to manage immense downhole temperatures, how to design robust drilling equipment, and how to transmit data through thick rock, are directly applicable to the future cryo-drilling missions that aim to penetrate kilometers of ice on worlds hundreds of millions of kilometers away. From these terrestrial superprojects, the focus now pivots to the modern concepts for autonomous cryobots, or melt probes. These are not your grandfather's drills. They are sleek, self-contained machines designed to melt their way through alien ice. A prime example is the TunnelBot, conceptualized by scientists and engineers at the National Aeronautics and Space Administration's Jet Propulsion Laboratory, a vision of robotic autonomy. These probes are envisioned as intelligent explorers, capable of analyzing their environment as they descend, making critical decisions without human intervention over vast cosmic distances. The most critical choice for these interstellar drills, arguably the very heart of their design, lies in their power source. At Jupiter, the Sun's light is incredibly faint, only about 4% of what we receive on Earth, making solar power utterly impractical. Instead, these probes would almost certainly rely on nuclear power. We are talking about compact, highly efficient energy systems, perhaps a small fission reactor, generating continuous heat and electricity from controlled nuclear reactions, or a next-generation radioisotope thermoelectric generator. These generators convert the heat from the natural decay of radioactive isotopes directly into electricity, providing a steady, reliable power supply for years, perhaps even decades. This constant internal heat is what allows the cryobot to melt a path, centimeter by centimeter, through kilometers of solid ice, creating its own tunnel as it descends. The mission architecture to deploy such a probe is a multi-stage ballet of precision engineering across the vastness of space. First, an orbiter would arrive in the Jovian system, meticulously surveying potential landing sites on the icy moon, mapping its surface topography, and searching for areas with thinner ice or signs of recent geological activity that might indicate an ocean closer to the surface. Once a prime location is identified, a lander would be carefully deployed, making a controlled descent to the moon's surface. This lander would then act as the delivery vehicle, deploying the cryobot onto the ice. The cryobot itself would begin its arduous journey, melting downwards through the ice shell. It would have to navigate autonomously, sensing changes in ice composition, density, and temperature, perhaps even detecting pockets of liquid water or embedded rock. As it melts, it would continuously analyze the ice layers, looking for organic molecules, signs of past geological activity, or any chemical signatures that might hint at life. Crucially, the probe would need a way to transmit its precious data back through kilometers of ice and then across 1 billion kilometers of space to Earth. One ingenious concept involves the deployment of a trail of communication pucks or repeaters, like a trail of breadcrumbs left behind by the cryobot as it descends. Each puck would relay data from the probe deeper in the ice to the one above it, until the signal reaches the surface, and then the orbiter, which would then beam it home. This is the story of an incredible technological leap, from drilling for geological secrets within our own planet to melting toward biological secrets 1 billion kilometers away under the crushing ice of alien worlds. For centuries, the search for life beyond Earth was confined to the realm of philosophical pondering or science fiction, a grand cosmic thought experiment. But what if the very act of searching for alien life is, in fact, the most profound journey of self-discovery we could ever undertake? Our grand scientific quest, spanning decades of unraveling cosmic mysteries, from the gravitational furnaces that forged warmth in distant worlds, to the invisible magnetic whispers that betrayed hidden oceans, to the chilling lessons learned beneath our own Antarctic ice, all lead us now to a single, profound question. It is a question that reaches far beyond the boundaries of planetary science, touching the very core of our existence. The upcoming interstellar endeavors, such as the European Space Agency's JUICE, or Jupiter Icy Moons Explorer, and the National Aeronautics and Space Administration's Europa Clipper, are not designed to find life directly. Their objectives are far more nuanced, more foundational, preparing the ground for future missions that might one day reach those liquid depths. These sophisticated probes, traveling hundreds of millions of kilometers across the void, are engineered to meticulously characterize habitability. They will precisely map the vast subterranean oceans, measure the thickness of the crushing ice shells that encapsulate them, ice that could be many kilometers deep, a barrier thicker than Mount Everest is tall, and methodically sniff for the faint chemical fingerprints of organic molecules within plumes that erupt into space from cracks in the surface. This is how we begin to decipher the chemical language of alien worlds. The common narrative often presents this as a simple binary: life found or no life found. But the reality and the scientific implications are far more intricate, more layered than a mere yes or no. What if, after centuries of searching, after deciphering every magnetic whisper and analyzing every particle of ice, we discover that all the necessary ingredients are present: abundant liquid water, complex organic chemistry, a powerful energy source from within the moon's core, yet life itself is conspicuously absent? What would that imply for our place in the universe? This great silence in a perfect cosmic petri dish would not be a failure. It would be a profound revelation in itself. Such an outcome would lend powerful, almost overwhelming support to what is known as the rare Earth hypothesis, suggesting that the spark of life, the initial genesis, is an exceedingly rare event, a cosmic miracle that occurs only under a confluence of extraordinarily specific and perhaps unique circumstances. It would imply that even when seemingly ripe conditions abound throughout the universe, the leap from chemistry to biology is an almost insurmountable one. Conversely, consider the inverse, a scenario that would ignite a firestorm of reevaluation across every field of science and philosophy. What if these distant, icy depths yield evidence of a second genesis? A biology completely unrelated to our own, one that evolved from a different tree of life, based on different, perhaps alien, chemistry, having sprung forth from an independent chain of events. This discovery, championed by visionary astrobiologists like Paul Davies, would not merely be astonishing, it would shatter the very notion of life's uniqueness in the cosmos. It would imply, with startling certainty, that the universe is teeming with life, that it is not an exception, but a predictable outcome of cosmic chemistry, a fundamental property of matter itself, arising wherever conditions allow. So, this monumental search is not merely a hunt for aliens, a simplistic quest for extraterrestrial beings dwelling beneath miles of ice. It is, in its most profound sense, a grand experiment, a cosmic mirror designed to calibrate our own existence within the vastness of the universe. Are we, the sentient beings on this blue marble, a cosmic fluke, a one in a trillion accident, an anomaly against the backdrop of an otherwise sterile cosmos? Or are we, in fact, a predictable, almost inevitable outcome of the universe's fundamental chemical and physical laws? Just one example among countless others. The faint, elusive signals we hope to receive from these distant, perpetually dark, and impossibly cold oceans are, in reality, not just data points from faraway worlds. They are echoes, profound and haunting, of our own deepest, most enduring questions about our place in the void, about the very meaning of life itself, and whether we are truly alone across the boundless cosmic sea.